let's start the next practice paper. So this is practice paper 5. Okay, so question number 1, and we have already finished in the last lecture our electrostatics. Okay, so till practice paper 4 there was electrostatics. Okay, this is related to current electricity. Okay. So the question says the effective resistance between the points A and B in the given network as shown in the figure. So you have to find what will be the effective resistance. Effective resistance means total net resistance offered by the circuit. Now you have to be very careful here, because here this is not like the way you are thinking. Here we will make use of Wheatstone bridge. Okay, so if you look at this, I can redraw this diagram, circuit diagram, like this. Let's see. So this is here, a resistance is there, and this is going to this part. Okay, this is, let's say, C point, and this is point D here, and from here I am connecting like this, and this is like this. Okay, and here it is like this, and here it is like this. This middle branch is extended here to F. This is F, so I am just extending it to F here. Okay, and again you can redraw this like this. This is your 4 ohm, and here over here it is 4 ohm, and here it is 4 ohm, and this is 12 ohm, and this is 8 ohm, and finally this is 8 ohm, and they both are connected here with 8 ohm and 8 ohm, and here in between there is P. Okay, so I've just redrawn it. Okay, now be very careful. If you look at this resistance value, this is 4, and what is this resistance value? This is also 4. This is how much? 8 ohm, and this is how much? 8 ohm. Again, here it is 4, 4, 8, and 8. Okay. Now be very careful. If the resistance, this is R1, this is R2, this is R3, and this is R4. We know that if R1 upon R2 for any Wheatstone bridge is equal to R3 upon R4. If this happens, let me repeat again. If R1 upon R2 for any Wheatstone bridge is equals to R3 upon R4 for such a circuit, then what is the current flowing in the middle branch? It has to be 0. Let me repeat once again, in case if you are not familiar with this balancing condition of Wheatstone bridge. Such a circuit, okay, which looks like this circuit, this part of the circuit is Wheatstone bridge. So if you have a Wheatstone bridge like this, in this circuit, if R1 upon R2 is equals to R3 upon R4, then this middle branch will have no current. And if there is no current in the middle branch, you can simply remove this middle branch. So let's remove this middle branch, and let's remove this also middle branch, and let's remove this branch also here. Okay, so you got a circuit like this. Why we removed it? Because there is no current flowing in the middle branch. And if there is no current flowing in the middle branch, there is no sense of keeping the resistors, right? So let's redraw it. So on the top, if we redraw, we know that this R1 and R3, they will be in series. So let's draw here this 4 ohm and that 8 ohm, they are in series. And here, this is the point C. I am putting here point C, and that is connected to, this is R2 and this is R4. They are also 4 and 8. Okay, fine. Here there is one wire going, here this is one wire going. Now this wire is connected to another resistor like this, and this is point A, and this is connected to another resistor like this, 4 ohm, and this is 4 ohm. And again this is connected to another Wheatstone bridge like this with 4-8, 4-8 combination. This is 4, this is 8. I hope this is clear. 4-8, 4-8. And what's over here? It's 8 ohm and 8 ohm. I hope this is clear to all of you. So I have just simply redrawn these. Okay, great. 4 and 8 in series combination, 12 ohm resistance. So let me draw the remove the previous diagram. So let me remove this previous diagram here, and let's redraw it. So 4 and 8, that's 12 ohm. So here 12 ohm is connected. Then again another 12 ohm is connected here. So 12 and 12, and that is connected from here, a 4 ohm and a 4 ohm. This is connected to again 12 and 12. So this is 12, and this is also 12, and that is connected again with the 8 ohm, and this is again 8 ohm, like this. This is A, this is B. I hope this is clear. Now 12 and 12 in parallel, what is the equivalent? Let me remove the previous diagram here. So here 12 and 12 both are in parallel. So what will be the equivalent? The equivalent of this one will be 6. So you have simply here a 4 ohm, a 6 ohm and an 8 ohm. 4, 6 and 8, and below also you have a 4 ohm, a 6 ohm and an 8 ohm. Okay, this is A and this is B. Now 4, 6 and 8, all three are in series, right? So what is the equivalent of the top one? The equivalent of the top one will be 18. This will be 18 ohms on the top. What will be the down one? 18 ohms. Now 18 and 18 in parallel. What will be the outcome? 9 ohms. So correct answer for this is option A, 9 ohm. Okay, let's see the next one. So this is your second one. Let's start with question number 2. This is question number 2 in the practice paper. So question number 2 says the current I drawn from the 5 volt source will be how much? Okay, so pay attention. This is another way of drawing the Wheatstone bridge. In case if you are not familiar with this, again let me show you that. Let's see here. This is our normal Wheatstone bridge which we usually draw. Okay, so pay attention on this one. Okay, this is A, this is B, this is C and this is D. Okay, so let's call this as point A. Now from point A, 2 wires are going, one resistance 10 ohm and one resistance 5 ohm. So let's call this as 10 ohm and let's call it as 5 ohm. Correct? Now from A, this 10 ohm, the other end is connected to another side. So 10 ohm, another is B. So this must be the B. Great. And 5 ohm, this is connected over here. So let's call this as D. So this is connected to D. Between B and D, there is 10 ohm. So this is 10 ohm. Now D, let's call this as C. So D to C, there is 10 ohm. And from B to C, there is 20 ohm. Okay. I hope this is clear. So in case if you have not seen such a diagram, this is same as Wheatstone bridge. Okay. Now the question is, if this is connected to a 5 volt battery, if you are connecting this circuit to a 5 volt battery, what is the current coming out? Now instead of using that complicated Kirchhoff's rule, you can directly see here that the ratio of R1 is to R2 is equals to R3 is to R4, which means 10 upon 5 is 2, this 10 upon this 5 is 2 and 20 upon 10 is 2. And if it happens to be true, what I said in the first problem, if the ratio of R1 is to R2 equals to R3 is to R4, then what we do? We simply remove this middle resistor. Why we remove it? Because this is called the balancing condition of a Wheatstone bridge, that says that if this condition is fulfilled, R1 is to R2 equal to R3 is to R4, then simply there is no current in the middle branch, always. And if it happens, then this 10 ohm and 20 ohm, 5 and 10 ohm, they will be drawn like this. Okay, now there is a big misconception. Students, they blindly look at these Wheatstone bridge diagrams. What they do is, like if they have given you instead of this 10, 5, 5, 10, okay, if they have just changed this value, let's say, and this is just an example I am taking, clearing the concept here only. Like in exam, if you get here 5 ohm and you get here 10 ohm, then 5 by 10 is not equal to 20 upon 10. And if it is not equal to that, then it is not balanced. And if it is not balanced, you can't draw this diagram. There will be some current and there you will have to use Kirchhoff's rule, voltage loop rule and like that. Clear? I hope this is clear. So let me remove this previous diagram and let's draw here. Let's deal with this. So here this 10 and 20 are in series. So net effective resistance is 30 ohm. And that is in parallel with 5 plus 10, which is 15 ohm. So what will be the effective resistance of these 30 and 50? 1 by 15 plus 1 by 30, and that will be equals to 1 by R equivalent. Usually students use this, okay, like in board exams. So we will not use this, we will directly use that formula. For parallel combination, the equivalent for 2 is R1 R2 plus upon R1 plus R2. This is faster one. Okay, for competitive exams use this. So 30 into 15 divided by 45. So 15, how much? 3s are 45 and 3 10s are. So what is the equivalent resistance? R equivalent in this whole circuit is 10 ohms. What's the voltage? 5 volt. What's the current? I equals to V by R. 5 by 10, that will be equals to 1 by 2, which is equals to 0.5 amps. Is there any option? Yes, option number B. Let's move to problem number 3. Okay, let's move to this one. Okay, so this question, quite important question because conceptually very rich. Okay, and you have to read this question very carefully, very carefully. Okay, so let me read here. Question says 12 cells each having same EMF and internal resistances are connected in series and are kept in a closed box. Some of these cells are wrongly connected. This 12 cell battery is connected in series with an ammeter, an external resistance R, and a 2 cell battery. Okay. 2 cells of the same type used earlier connected perfectly in series. The current in the circuit when the 12 cell battery and 2 cell battery add each other, okay, is 3 amps, and it is 2 amps when they oppose each other. Then the number of cell in 12 cell battery that is connected wrongly is. Okay. Now some of you must have understood the concept, what question is saying, and some of you are still struggling that what this huge paragraph is saying. Okay. So let's go step by step and understand the whole concept behind this problem. Very beautiful problem. How many initially? First thing, it's saying there are 12 cells. So I'll not draw all the 12 cells. Okay. Let's read the first line up till here. So there are 12 cells each having the same EMF and internal resistance are connected in series and are kept inside a closed box. Okay. So I am making a box over here. A box. Okay. What does this box represent? These 12 cells. Okay. Out of which some are correctly connected, like positive to negative like this in series combination. Some are wrongly connected, negative somewhere, positive somewhere, negative like this. Okay. How many total are there? 12 are there. Okay. So how many are there in cells in this? 12. I hope no one has any doubt in this, understanding this part. Okay. So you simply took 12 batteries, a simple battery, like you can do this experiment at home also. Okay. You are taking simple batteries, that remote batteries. Okay. How many batteries? 12 batteries. Okay. And you are randomly connecting this. Okay. Randomly connecting means sometimes you are connecting positive with the negative terminal, negative with the positive terminal, and sometimes you are randomly connecting negative, positive. Okay. We know that current will not flow in such situations, but we are connecting it wrongly also sometimes. Okay. So some cells are wrongly connected. Okay. How many we don't know. We have to figure out at the end. Okay. Now this setup, this 12 cell battery, this is 12 cell battery which is connected inside a box. Okay. This is connected in series with an ammeter. So let's connect here an ammeter over here. Let's say this is an ammeter over here. Okay. We'll go very slow in this problem because this is important. This is connected to an ampere. Okay, ammeter, that's telling you the current, and an external resistance R. So let's connect here with an external resistance R. Okay. R, and a 2 cell battery. 2 cell battery means now this is connected to, okay, let me connect here like this. 2 cell battery. 2 cell battery. 2 cells of the same type used earlier, connected perfectly in series. Okay, this is connected perfectly in the series. Till which point we have done with the diagram? This point. Okay. In case if you understood this, very good. If you have not understood, let me repeat again for you. Okay. We had 12 batteries and these 12 batteries are connected randomly. Some of them are in perfect order. Some of them are in random orders. Okay. We don't know what is the order. Okay. Then that is connected to an ammeter, an external resistor capital R. Okay. And 2 other batteries having same EMF. Okay, great. So let's assume that these 12 batteries, they have EMF E. Let E and R, small r, E is what? EMF and internal resistance. Okay, so each of these 12 batteries, let's say E is the EMF and R is the internal resistance of the battery. Okay, great. So if there are 12 cell battery, now please concentrate. What will be the total EMF of these 12 batteries? So 12 times E. And let's say N batteries are connected wrongly. Let me repeat. If there are N batteries, let N batteries or cells, not battery, let me use this word cell. N cell, because battery cell combines to form a battery. N cells are connected wrongly. If N cells are connected wrongly, so how many cells which are right connected? 12 minus N. What's the equivalent EMF of this? 12 minus N into E. These are the batteries which are connected correctly, minus how many of them are wrongly connected, N, and each N has what EMF? E. This will be the equivalent EMF of the closed box. Let me put it as E. Let me repeat again. If there are N batteries, N cells which are wrongly connected, then how many are right in a perfect order? 12 minus N. So what will be the equivalent EMF of those rightly connected cells? 12 minus N times E. And what's the equivalent EMF of wrongly connected? NE. So this and minus. Why minus? Because they are wrongly connected, right? They are not adding up to the equivalent voltage. Okay. So can we simplify it further? We can write it as 12 minus 12E minus NE minus NE. Let me minimize and make some space here. So what will be the equivalent EMF of the box? It will be 12E minus twice of NE. I hope this is clear. This is equation 1. Next is, if this is your equivalent, what is the equivalent resistance of all these 12 batteries? That will be 12 times R. 12 times R is equivalent resistance of all these batteries connected in the box. Okay, great. Next, let's read now from this part. The current in the circuit when the 12 cell battery, which is this box, and the 2 cell batteries, which are these two, are adding each other is 3 ampere. Okay, which means they are connected in the same configuration. Then the current is 3 amps. And if it is in the opposite configuration, then it is 2 amps. You have to find the number of cells in the given package which are wrongly connected, right? Okay. So what we will do here? So first of all, we will find current. What's the current? I is equals to E upon R plus R. Remember this relation? This is the relation we have done in this chapter, where E is the EMF of the battery upon total EMF of the battery upon R is the internal resistance, the small r, and capital R is the external resistance. So here, what will be the current? So current is 3 amps. Okay, great. And what is the EMF of this whole circuit? Let me repeat again. What is the EMF of this whole circuit? So there are 12 these batteries and 2 these batteries. So these 12 are contributing equation 1, which is how much? Which is 12 minus 2n times E. This is the box 1. And if these 2 batteries are in accordance in the same manner connected, then it will be 2 times E. So from where you got this 2E? Each battery here is alike. They have written here, see, the 2 cells of the same type used earlier, connected perfectly in the series. So it will be adding up. It is adding. So 2 times E upon, pay attention to the internal resistance. So internal resistance from here is 12R. From these 2 batteries, it will be 2R, and an external resistance is there, that is capital R. Equation. I hope this expression is clear. Okay, now if they are wrongly connected, then what will change? Then this 3 current ampere is decreased to 2 ampere, and here the this value EMF is 12 minus 2, and same thing here, but this is wrongly connected to this, which means the polarity of these are changed. These two cells polarity is changed, so it will be minus 2E here, whole divided by internal resistance, and everything remains same. So 12R plus 2R plus R. This is equation number 3. Anyone has any doubt in equation 2 and equation 3? Speak up. I am removing this A's too, so that you don't get confused. Okay, so that was 2 and that was 3. What we will do now, we will divide equation 2 and equation 3 and find the value of n. So when we divide both, the denominator cancels out. Okay, so this will be 3 by 2, that will be equals to 12 minus 2n E plus 2E whole divided by 12 minus 2n E minus 2E. Correct? I hope this is clear. Let's take E common out and cancel from the numerators and denominators. So what we left with here? We left with here 3 by 2. Let me solve it here. 3 by 2 is equals to 12 plus 2, 14 minus 2n, and denominator 12 minus 2, 10 minus 2. Let's cross multiply. 30 minus 6n is equals to 14 to the 28 minus 4n. So let's take 28 on that side, it will be 2, and let's take 6n on the other side, 2. So n equal to 1. How many batteries are wrongly connected? 1 battery. Okay, great. Let's move ahead and see the fourth question. So the next question, fourth question, is this one. Okay, so fourth question in the practice paper is, let's read it. A cell in secondary circuit gives null deflection for 2.5 meter length of potentiometer, okay, having 10 meter length of the wire. I hope you are familiar with these things because experimentally you have done potentiometer. So length of the wire is 10 meter, length of whom? Length of the potentiometer wire. And what is this 2.5 meter? This is that point at which you press the jockey to get null deflection. No current is flowing in the circuit, right? Okay. If the length of the potentiometer wire is increased by 1 meter without changing the cell in the primary, what will be the position of the null point? Very simple question. Okay. So what is important concept of a potentiometer? Listen very carefully. What is the something which remains constant for a given potentiometer? Potential gradient phi. What is potential gradient phi? That will be equals to voltage given by the primary cell upon length L. Let me repeat again. If you are having a particular cell connected to a potentiometer, if you are not changing the primary cell and if you are not changing the potentiometer, you are keeping the same, okay? And if you are changing the length or any other parameter, then what will remain constant? Phi. Phi is what? Potential gradient. So E is nothing but phi into L. We know that. And from here only, if you remember, we used to find the equation E1 upon E2 equal to L1 upon L2, right? So we will make use of that only. Okay. So let's say this will be, okay, so let's find the potential gradient. So phi is equals to, let's say the EMF of the initial one is E, okay, so E by L, length is 10 meter initially, right? Okay. Now since the secondary circuit gives a null deflection at 2.5 meter length of the potentiometer, okay, so what we can say? We can say that E will be equals to, what is phi? Be very careful, this E is what? This E is different from this E now. Let me put here E naught so that you don't get confused. E naught is what? Primary cell. E is for secondary cell. That will be equals to E naught upon 10 into length is what? Length is 2.5. Let me repeat again. This E is the, it will also follow the same thing. Phi will remain constant. So E will be equals to phi into L, and phi is what? E naught upon the initial length of the potentiometer. So E equals to E naught by 10 into 2.5. Now in the second case, when the length increases, so what will be the new length? L prime, that is 10 plus 1, that is 11 meter. So what's the potential gradient now? Length change, because phi is dependent on L. So this will be phi prime. That will be equals to what? It will be E naught by new length. What's the new length? 11. Correct. So can we find the new balancing length for this circuit? Yes. What will be this new one? E is equals to phi prime into the new length. We are finding L prime. Sir, what about this E? Why it is not E naught? E prime. This is not E prime because they have not changed the primary nor the secondary circuit. They have simply changed the length L prime in this case. So phi prime here is nothing but E naught by 11 into L prime. And what's our E? We got it in the previous case. E naught upon 10 into 2.5. Let's cancel this with this and cross multiply. So 2.5 into 11 upon 10. Let's remove this. It will give you 100. 25 folds is equals to L prime, and L prime equals to 11 by 4. 11 by 4 means 4 2s are 8, and you left with 3 7 5. So option C. Correct answer is option C. And okay, the question says in the given figure, okay, electric circuit has been shown. The value of the current I you have to find. What you have to find? You have to find the value of current I. Let's start from the left side of this. Each point is treated as a junction. Each point is treated as a junction. So this is one junction here. This is another junction over here. This is next junction over here. Let's call this junction as A. Let's call it as junction B. Let's call it as C. Let's first deal with junction A. So what is our junction rule? Our junction rule says that the current entering the junction 2 plus 2 must be equal to the current leaving the junction, which is from A to B. So let's call it as X. X is the current going from A to B. So it must be 4 ampere. I hope this is clear. Okay. And in case if you don't know junction rule, just assume that this is water pipes and these are water. So from here 2 liter is coming, from here 2 liter is coming. So how many liters will go from A to B? 4 liters. Very simple. Now 4 liters of water is coming from here and 1 liter water is coming from there. How many liters will go down? How many liters will go from B to C? Sir, 5 liters. And 5 liters are coming here, but look at this arrow. This arrow is opposite, which means 5 liters is coming from top and 1.3 liters are going away. So how many liters left? 3.7. I hope this is clear. Very simple question. Okay, let's move to our next problem, that is 6th one. So 6th one here, it is there are 3 resistances, 5 ohm, 5 ohm and 6 ohm are connected as shown in the figure. 5 ohm, 5 ohm and 6 ohm, they are connected in the figure as shown. Okay. If the point S divide the resistance 6 ohm into 2 equal halves, okay, the resistance between point P and S is great. So what we will do here is we'll just open this. So let's see how it will look like if we open this. Okay. So point S is dividing the resistance 6 ohm into 2 equal halves. So we will first we will redraw this first and then we will open it. Okay. So this is point P, this is point S, and here I am drawing one resistance, that is 3 ohm, and here I am drawing another one, this is 5 ohm and this is 3 ohm. Okay. From where I got this 3 ohm, 3 ohm? I got this 3 ohm, 3 ohm because this S, from S it is dividing the resistance 6 ohm into 2 equal halves. So this must be 3, 3, right? Very simple. Now let's hold it from these 2 points P and S and open the circuit. So what will be here? 5 and 3, this will be 8. Okay, let's draw it this way only so that it becomes, so this is P and this is S. This will be 8 ohm and this will be 8 ohm, right? 5 and 3 series, 5 and 3 series, so this is 8 ohm, this is also 8 ohm. And this 8 ohm are in parallel. So what will be the equivalent? So simple, 4 ohm. Let's move to question number 7th. Okay, so our next question is this one. So 7th one says, in the given circuit, the ammeter shows 5 amps of current, voltmeter shows 250 volts, and the internal resistance of the voltmeter is 2500 ohm. Then what will be the value of R? Okay, let's start with this. So pay attention, very simple yet very important 10th standard concept. First of all, let's make it easy by drawing a resistor, small resistor, so that you don't forget about this resistance. So what is this resistance value? This is 2500 here, 2500. So first of all, what's the current across the ammeter? 5 amps. 5 amps is the current. Now if 5 amps of current is going from the ammeter, what will be the current across the resistor? We don't know. What is the current across the voltmeter? We don't know. Will it be same? No, we don't know. Why we don't know? Because resistances may or may not be same. Clear? So let's first find what is the current across the voltmeter. How do you find the current across the voltmeter? Voltmeter is saying that it is 250 volt and it has this much resistance. So if I divide both, I will get the current across the voltmeter. So let's cancel out this with this. 25, 10, 1 by 10 amps. Let me repeat again. The voltage across the voltmeter is 250 and the resistance of the voltmeter is 2500 ohms. If I divide the voltage by resistance, I get the current across the voltmeter, which is 1 by 10 amps. What is the current coming out of the ammeter? 5 amps. Out of which 1 by 10 amps is going to the voltmeter. Can I find the resistance current which is across this resistance R? Yes. What will be IR? That will be 5 minus 1 by 10. Sir, how we know that? If 5 liter water is coming here and some 1 by 10 liter is going here, then how much is going in the remaining one? There is no other branch. So it has to be 5 minus 1 by 10 amps. So that will be 10 5 is 50 minus 1, 49 by 10 amps or 4.9. Logically true. 1 by 10 is 0.1 amps. So 0.1 is going down. So how much is going on the top one? 4.9. Correct. So voltage, current across the resistance R is 49 by 10. Do we know what is the voltage across this resistance R? Yes. What is that? 250 volt. But sir, it's not written anywhere. But you should know that voltage in case of parallel combination remains the same. So this voltmeter is showing the voltage across this resistance itself. So voltage across this resistance is 250 volt. And current across this one, we already found 49 by 10. Can we find the resistance value? Yes. R will be equals to voltage across the resistor upon the current across the resistor. So this will give us here VR is 250, IR is 49 by 10. So 10 goes on the top, 2500 divided by 49. So let's calculate it. Let me calculate using calculator for a minute to save time. So 2500 divided by 49. So it's 51.02. Is there any option for 51.02? Yeah, 51 is there. So correct option is option D. Let's move ahead with the next one. Question number 8 in the practice paper 5. So this is our practice paper 5, question number 8. Okay. So the question says a meter bridge is set up as shown. Okay, great. To determine unknown resistance X, this is unknown resistance over here X, using a standard 10 ohm resistor, fine. The galvanometer shows null point when tapping key is at 52 centimeter. 52 centimeter. Okay, the end corrections are 1 centimeter and 2 centimeter respectively. for the ends A. So from here the end correction is 1 centimeter, and from B it is 2 centimeter. Okay. The determined value of x you have to find. Great. So first of all, you should know the formula. The formula for meter bridge is any resistance. Let me call this as A. Let me call it as B. So A upon B should be equals to L upon 100 minus L, because it's a meter bridge. So what is the length of this AB? 100 centimeter. Let me repeat. What is the length of AB? 100 centimeter. So length L is that point at which you are finding null deflection. So if this is L, what will be the other one? Other one will be 100 minus L. And A is the resistance connected in this part, and B is the resistance connected in that part. So let's make use of that. Sir, but what to do with this end corrections? End corrections is the error in the measurement. So let's see what we do with that. So X is connected across A, upon B it's 10 ohm, length across A is 52 centimeters, so 52 plus 1, that's end correction, we are adding 1, okay, whole divided by what's 100 minus length? 100 minus 52, and what's end correction across the other end? Plus 2 centimeters. I hope this is clear. Okay, so this is the correction. We have to add 1 and 2 on both the sides. Okay, great. So this will be x will be equals to 10 into 53 upon 100 minus, okay, minus 52 and plus 2, minus 50, so 50 here. Let's cancel this with this. So x will be 53 by 5. Let me now divide it. 5 ones are 5, okay, and 0.6. Option B it must be. Let's move to the 9th one. Okay, great. 9th one. Beautiful problem and very, very important for conceptually very rich. Okay, let's move to this one. Question says two wires of equal diameters. Two wires of equal diameters. So D1 is equals to D2. Resistivity rho 1 and rho 2. Lengths L1 and L2 are joined in series. What will be the equivalent resistivity of the combination? They are not asking resistance. What they are asking? Equivalent resistivity of such a combination. So what you have to do? You have a wire here and you have another wire here. Correct? Let's figure out the resistance of the first wire. So R1, which will be equals to rho L by A. So this will be rho 1 L1 upon area pi R square. And what is R? Let me keep it R1 square, and let me substitute now here rho 1 L1 upon pi. Resistance is what? Radius is what? Diameter D1 divided by 2 whole square. Correct? So what will be our resistance? 4 times rho 1 L1 upon pi D1 square. Anyone has any doubt or not understood this part? Speak up. Great. Let's find R2. So similarly, the resistance value of the second wire will be 4 times rho 2 L2 upon pi D2 square. Let's remove this D2 and D1 because they both are equal. Let's call it as D. So let's call it as D because they are equal to avoid any confusions. And once you have found your resistances values, your equivalent resistance R will be equals to R1 plus R2. Correct? This is equivalent resistance of these two wires connected in series. So what is R1? 4 rho 1 L1 upon pi D square plus 4 rho 2 L2 upon pi D square. And this equivalent resistance for any such systems, for equivalent resistance for any such system, for a single wire, 10 wires, 5 wires, it should be equals to what? It should be rho L by A. Correct? here rho will be what? Equivalent resistivity, L is the equivalent length, and A is the equivalent area. Okay. Since they both have same diameter, this equivalent area will be similar. So what we can write it? We can write it as 4 rho L1 plus L2, that will be the total length when they are connected in series, whole divided by pi d square. Anyone who has not understood this part, and the right hand side it will be 4 rho 1 L1 upon pi d1 pi d square plus rho 4 rho 2 L2 upon pi d square. Yes, if you are not clear with this thing, speak up. Let's divide the whole equation with pi d square, and let's see what, and 4. Let's see what we left with. Rho, what is this rho? This is the equivalent resistivity, that will be into total length L1 plus L2, and that will be rho L1 plus rho 2 L2. Everything else cancelled. So resistivity, equivalent resistivity of two wires having length L1 and L2 connected in series will be this. Is there any option? Yes, option A. Okay, let's move to the last problem for this practice paper 5. Two cells, first is EMF E1, second is EMF E2, are connected as shown in the figure. Okay, great. So E1 is here connected and E2 is connected over here. When a potentiometer is connected between A and B, the balancing length of the potentiometer wire is 300 centimeter. Pay attention. You are connecting between A and B. On connecting the same potentiometer between A and C, this is here and here, the balancing length reduces to 100 centimeter. What is the ratio of E1 is to E2? Very simple question. So first of all, E1 will be proportional to 300. Sir, why? See, a potentiometer will be having its own primary cell. These E1 and E2 are what? These are the secondary cell. So just now we have done in today's lecture one of the problem on that. So E is equal to phi L. Phi is what? Gradient, potential gradient. That phi is dependent on what? Primary cell. So E, if phi is constant, okay, E is proportional to 300. Correct? So if E1 increases, this length also increases. Okay. And in case of AC, when you are connecting A and C, what will be the effective voltage? Look at this. This is negative connected to negative. So effective voltage will be E1 minus E2. And that will be proportional to 100. Correct? Like if you are not familiar with this proportional thing, let's make it in a similar way what we did in the previous problem. So E1 will be equals to phi L, and E1 minus E2 this time will be equals to phi into L. Phi is what? Potential gradient. On what potential gradient depends? Primary cell voltage E0 and the length of the potentiometer, right? We did a problem on that. Let's divide these two. We will get here what? We will divide this with this. So this will be E1 minus E2 divided by E1, and that will be equals to 100 upon 300. Let's separate them. 1 minus E2 upon E1 will be equals to 1 by 3. Let's take it on the other side. So 1 minus 1 by 3 is equals to E2 upon E1. So 2 by 3 is the ratio of E2 upon E1. They are asking the ratio of E1 is to E2. So E1 upon E2 is equals to 3 by 2. Option D.